Have you ever looked up at the sky and wondered why it's blue? Or why sunsets are drenched in reds and oranges? Well, the answer lies in an amazing physical phenomenon called Rayleigh scattering, and it's more than just an explanation for pretty skies. In this video, we'll dive into the history, the science, the applications, and the lasting impact of this concept. Stay tuned as we explore the blue mysteries above us. The story of Rayleigh scattering starts with one man, John William Strutt, better known as Lord Rayleigh. In the 19th century, Rayleigh was deeply interested in understanding how light interacts with small particles in the atmosphere. Back in the 1870s, he published a groundbreaking paper titled On the Light from the Sky, Its Polarization and Color, where he explored the scattering of light by small molecules in the atmosphere. At the time, scientists knew that light could be bent and refracted, but no one quite understood why the sky appeared blue. Through meticulous experiments and observations, Rayleigh discovered that the colors in light are scattered by particles in the air. His work provided the first clear explanation of why the sky looks the way it does and, in time, shaped the study of optics and atmospheric science. In 1904, Rayleigh was awarded the Nobel Prize in Physics for his work on the density of the Earth's atmosphere, which was built upon his earlier findings related to the scattering of light. But what exactly is happening when light interacts with these tiny particles in the air? Let's break it down. Sunlight, or white light, is a mixture of all the colors of the rainbow, each with a different wavelength. When sunlight enters Earth's atmosphere, it encounters particles that are much smaller than the wavelength of visible light, specifically nitrogen and oxygen molecules. Because these particles are so small, they scatter the shorter wavelengths of light, like blue and violet, much more efficiently than longer wavelengths like red or yellow. Here's where the magic happens. The shorter wavelengths, like blue and violet, scatter in all directions when they interact with these molecules. However, our eyes are more sensitive to blue light and less sensitive to violet, which is why we see the sky as blue instead of violet. At sunset or sunrise, the light has to pass through more of the atmosphere, which scatters the shorter wavelengths even more. This leaves the longer wavelengths, like red and orange, to dominate, giving us those breathtaking sunset colors. But it's not just about the sky being blue or a sunset being red. Rayleigh scattering is a key player in many natural and scientific phenomena. To understand the underlying physics a bit more, Rayleigh scattering can be described mathematically. The intensity of scattered light is inversely proportional to the fourth power of the wavelength. In simpler terms, shorter wavelengths, like blue, scatter much more than longer wavelengths, like red. This explains why the sky is primarily blue, and why the colors of a sunset are dominated by the reds and oranges. The equation shows that blue light is scattered much more efficiently, explaining its dominance in the sky. This relationship is vital to many atmospheric studies, as it helps scientists quantify air quality and atmospheric composition. So, Rayleigh scattering isn't just a phenomenon that gives us a beautiful sky. Its implications are felt in a variety of scientific fields. In astronomy, Rayleigh scattering helps scientists study the atmospheres of distant planets. By analyzing how light from stars and other celestial bodies interacts with a planet's atmosphere, scientists can determine the composition of those atmospheres and learn about distant worlds. In environmental science, Rayleigh scattering is used to monitor air quality. By measuring the scattering of light in the atmosphere, researchers can detect pollutants, aerosols, and even gauge levels of particulate matter in the air. This helps in combating air pollution and studying climate change. Rayleigh scattering is also pivotal in the field of optics, particularly with lasers. The scattering effect is used in light-based diagnostic tools, such as in medical imaging and laser treatments. Understanding how light behaves when it interacts with particles allows scientists to develop new technologies for imaging tissues, detecting diseases, and even enhancing laser therapies. You may have also heard of the Raman effect, an extension of Rayleigh scattering that is used in spectroscopy to identify the composition of materials. By measuring how light is scattered off a material, scientists can detect specific molecular vibrations, which makes this principle incredibly useful in chemical analysis. Rayleigh scattering's impact extends beyond labs and classrooms. it has real-world applications that affect our daily lives. In weather forecasting, for example, scientists use satellite images that rely on light scattering to detect changes in the atmosphere. This helps with predicting weather patterns and understanding how pollution spreads. Even in our day-to-day experience, we interact with technologies that depend on Rayleigh scattering. The internet and telecommunications systems use fiber optic cables, which rely on light scattering for transmitting information across long distances. So, next time you look up at the sky and marvel at its color, or gaze at a beautiful sunset, you'll know that Rayleigh scattering is behind those mesmerizing scenes. From astronomy to air quality studies and medical technologies, this simple but profound concept plays a huge role in our understanding of the world. If you enjoyed this deep dive into Rayleigh scattering, don't forget to hit that like button, subscribe, and turn on notifications for more fascinating science explanations. Until next time, keep exploring the wonders of the world around you.